So 6 asks us to prove that the summation of mu of d has to equal 2 to the omega n, where d divides into every n. So let's recall a couple things. So first, that mu of n equals -1 to the omega n if it's square free, and 0 else otherwise. So let's define our function capital F of n such that it's equal to the summation of d dividing n of mu of d. So remember, f is multiplicative, so it follows that if we can prove f of ps equals 2, then we're done. Because since we're looking for 2 to the omega n, we can just multiply the rest by factors of 2. So how do we do this? So, well, f of p to some exponent s, well, we can rewrite that. So we're basically trying to find this notation for all the divisors that divide into p to the s of mu of d. Well, now just write out all the factors that divide into p of s. Well, that's just mu of 1, mu of p, mu of p squared, all the way to mu of p of s. And it should be absolute value. So recall that, well, anything above p squared, so p cubed, p fourth, p to the 107th, p to the s, that's not going to be square free. So as a result, these terms drop out. These are going to be 0. So now what are we left with? Well, mu of 1, what is that? Well, how many prime divisors divide into 1? 0, right? So that's just going to be 1. With prime, how many distinct prime divisors divide into a prime? Well, that's also just going to be
1.
I think that's the value.
I feel like it's not going to get edited out.
So recall that how many prime divisors divide into a prime number? That's just me 1. So for 3, only 3 divides into that. So that means omega of n equals 1. So that's going to give me -1. But recall that this is the absolute value. So it's really like absolute value of mu of 1 plus absolute value of mu of p plus absolute value of mu of p squared, etc. So absolute value of 1 plus absolute value of -1, and that's going to give me 2. For 7, it asks me something similar. It asks that if n is even, then prove that the summation of d dividing n of mu of d times phi of d is 0. So let's recall that f is multiplicative. So f of n of the summation of d dividing n of f of d is also multiplicative. So since mu of phi and since mu of d and phi of d is multiplicative, and so is capital function f. So all we really need to do is prove that f of 2 of s, where s is some exponent, equals 0 for all s greater than 1. Same thing up here for all s greater than 1. So as a result of this, if we can just prove this for any exponent s, then we would prove that this works for any case such that n is even. So again, let's divide this up. So that means that f of 2s equals the summation of d dividing 2 to the s, the mu of 2 to the s, times 5 to the s. So now let's just separate that out into all its divisors. So we're trying to figure out, let's separate that out. So mu of 1 times phi of 1 plus mu of 2 times phi of 2 plus mu of 2 squared times phi of 2 squared. And then we're going all the way up to mu of 2 of s times phi of 2 of s. So again, recall, just like last time, anything above with an exponent 2 or higher, that's not going to be square free. So as a result, this goes to 0. So then we're just left with these two terms. So what's mu of 1? That's just 1. Phi of 1 is just 1. Mu of 2, that's going to give me negative 1. And phi of 2, that's going to give me 1. So that's 1 minus 1, and that gives me 0.